Hello everyone and welcome back to yet another video from my channel Interactive Education, running for the best education possible from the student to the student for a better experience. And today we will be continuing the series on redox reactions, and we're going to discuss the other rules for writing oxidation number of various elements. I'm going to carry on from where I stopped in the last video. So in the last video, we discussed the oxidation number for hydrogen, oxygen, alkali metals, alkaline earth metals, and elements in free state. So in this video, we're going to continue with the same, that is oxidation number, right? So there are some other elements for which we write the oxidation number, and it's important for us to know their rules as well. So let's go on to the next element or the next kind of rule I'm going to discuss, and that's for nitrogen, right? Nitrogen. Now nitrogen is an element, symbol N, atomic number 7. And atomic number 7, nitrogen, is in group 15 of the periodic table. It's in group 15 of the periodic table. Now this nitrogen exhibits various oxidation states, but there is a particular range of the oxidation states for nitrogen and its other group elements, right? And the range for group 15 elements and their oxidation numbers is from -3 to +5. This is the range of oxidation numbers from -3 to +5. So nitrogen and other elements of the group 15 of the periodic table can have oxidation number in the range from -3 to +5. Any number, fractional or integral, from -3 to +5, right? Let's take some examples to understand this. The first and foremost example is that of ammonia, NH3. In ammonia, nitrogen forms 3 covalent bonds with 3 other hydrogen atoms and has a lone pair. Right, so this is the structure of ammonia, NH3. So ammonia, NH3, here nitrogen has 3 covalent bonds with other hydrogens, and you know nitrogen is more electronegative than hydrogen. In fact, nitrogen is the third most electronegative element in the periodic table after fluorine and oxygen. So hydrogen gets a partial positive charge, nitrogen gets a partial negative charge, and this occurs for each and every bond. So as a result, nitrogen gets 3 units of minus partial positive charge or negative partial negative charge. Excuse me. Nitrogen gets 3 units of partial negative charge, and as a result, it will get an oxidation number of -3. That is 3 units of partial negative charge. All right. Another example we can take is that of hydrazine, and hydrazine is N2H4. Okay, N2H4 is hydrazine. The structure of hydrazine is nitrogen forming 2 covalent bonds with hydrogen, then a single bond with another nitrogen, then with hydrogen, and then with hydrogen. Again, lone pairs are present on each of the nitrogen atoms. So this is hydrazine. Okay, it is hydrazine. So in hydrazine, if you see, nitrogen again forms 3 covalent bonds. However, only 2 of the bonds are polar because the nitrogen-nitrogen bond is non-polar, right, between similar elements. So only the 2 NH bonds are polar. As a result, partial ionic character is seen only in these 2 bonds. So hydrogen gets a partial positive charge, nitrogen gets a partial negative charge. This nitrogen again gets a partial negative charge, gets a partial positive charge. This nitrogen also gets a partial negative charge, this hydrogen gets a partial positive charge, and this nitrogen again gets a partial negative charge, this hydrogen gets a partial positive charge. As a result, each of the nitrogen atoms have 2 units of partial negative charge. How many? 2 units of partial negative charge each. So oxidation number of nitrogen for each nitrogen atom comes out to be -2. Clear? So this is how we calculate the oxidation number of nitrogen in various compounds. But it can be any number from -3 to +5. Here I gave you example of -3 and -2. It can also exhibit positive oxidation number, as in the case of N2O5. And this is obvious because oxygen is more electronegative than nitrogen. It is obvious it has to be like that. Oxygen has -2 oxidation state here, no peroxide linkage. So you know that then hence the oxidation number of nitrogen will be +5. And this is the highest you can see, right, for nitrogen. So it can show it can show positive charge in case of molecules or compounds where there is a more electronegative element than nitrogen, right? So I hope nitrogen is clear. Basically, the range is -3 to +5. In case you have a compound where the nitrogen oxidation number comes other than this range, you can be sure that there is some exception involved. It can be either a peroxide linkage, it can be something else. So there is some or the other uh, exception involved if this case occurs, that it comes out of this range, that's it's less than -3 or greater than +5. In that case, there is some exception involved. Probably it should be a peroxide linkage, right? Clear? So let's move to the next element for which we're going to discuss the oxidation numbers, and that is for halogens. Now your halogens are group 17 elements, that is the fluorine group, right? So they are group 17 elements. Group 17 elements, that is which group? Fluorine group. But here we consider only elements other than fluorine. So we're going to talk about chlorine, bromine and iodine. We're not going to discuss about fluorine because we discussed about fluorine earlier, where we said that in combined state, because of its high electronegativity, we say that fluorine always has -1 oxidation state in all its compounds, right? But for chlorine, bromine, iodine, if we consider, the range can be any number from -1 to +7. -1 to +7, and this can be easily explained using orbitals, using subshells, right? If you take the example of chlorine, atomic number 17, and its electronic configuration on the outer shell, right? In the outer shell, that is the outermost electronic configuration, that is 3s2, 3p5 and 3d0. If you do its electronic configuration in terms of orbitals, you will see that its outermost electronic configuration is like this. So now if you check this and now draw the different subshells. So this is the 3s subshell fulfilled. This is your 3p subshell with one electron less, and this is your vacant d orbital. It's a p block element in the third period, hence it can have a vacant d orbital. So this is your 3s2, this is 3p5 and this is 3d0, right? So when you excite this state, right, you can see that here how many unpaired electrons are there? 1, right? So unpaired electrons in the ground state is 1. But when you excite these electrons, some electrons will move to the vacant d orbital, right? Some electrons, they will get unpaired and move to the vacant d orbital. So as a result of this, right, so they will get unpaired. The paired electrons get unpaired, they move to vacant d orbitals, and you will get in the end the maximum number of unpaired electrons you can get. A maximum number of unpaired electrons that you can get, okay, is so, right? So one here because it gets unpaired, this also gets unpaired, then one here, then one already unpaired, one here, and one here. So 1, 2, 3, 4, 5, 6, 7. So unpaired electrons in excited state is 7. So here you can see that it can go from any number from -1 to +7. This is the reason, right? This is the reason why, because the maximum number of unpaired electrons you can get is 7 in case of chlorine, bromine and iodine. This is not possible in case of fluorine, because number one, it's very electronegative, and second is that it is very small. Fluorine is a very small atom, one of the smallest atoms in the periodic table. So that is why it is not possible for us to excite electrons, and there is no vacant d orbital as well, right? Clear? So you can see that because of this electronic configuration, you can see maximum number of unpaired electrons is 7 and the number of unpaired electrons in ground state is 1. So it can easily gain an electron and form a fulfilled subshell, or it can lose these 7 electrons and form plus 7 state. So -1 to +7. Any number between these is possible. Clear? So because of this, you can explain the range of the values of oxidation numbers of halogens, right? And in various elements you will see, in various compounds you can see this range coming, right? For example, let's take chlorine as an example, right? Because bromine and iodine is simple to explain, so you just understand chlorine also. For example, HCl, in HCl this will gain a partial positive charge, this will gain a partial negative charge, so chlorine has -1 oxidation state, right? Another example is that of HOCl, which is chloric acid. In chloric acid, you will see that this gains a partial negative charge, this gains a partial positive charge. So chlorine, again, this partial -2 negative charge, this will partial 2 negative charge because there are 2 bonds, right? And these two both are polar. So this is partial positive charge and here also partial negative charge. So in total, chlorine has an oxidation state of +3 because it has 3 units of partial positive charge, right? Chlorine being a halogen can still exhibit positive oxidation state, unlike fluorine, right? So that's also something to note here. Then you can also take the example of perchloric acid or hyperchloric acid. For example, HOCl. This is perchloric acid, okay? So in perchloric acid, you will see that oxygen has minus sigma minus delta, then minus delta, here also plus delta. This is again plus delta. From here you will get plus 2 delta. From here you'll get plus 2 delta because there are 2 covalent bonds and chlorine is more electropositive than oxygen and plus 2 delta. So total is plus 2 plus plus 2 plus plus 2, that is plus 6 plus 1, this is plus 7. The oxidation state of chlorine is plus 7 in perchloric acid. Clear? And what is the formula? You know the formula for this? It is HClO4, perchloric acid. And it is one of the strongest acids, perchloric acid. Clear? So this is the explanation of the oxidation number of halogens in various compounds. Clear? So that's with your halogens, chlorine, bromine and iodine. Next we come to sulfur. Let's discuss sulfur and other group 16 elements. That's the oxygen group, right? So we've already discussed separately for oxygen, so I'm not discussing oxygen here. But sulfur and other group 16 elements have a special range, right? They can get any oxidation number from -2, the range is from -2 to +6. Any oxidation number from -2 to +6, right? So here also you can explain this easily. If you take sulfur with atomic number 16 and its outermost configuration is 3s2 3p4 3d0. So again, let's draw the orbitals. So in the orbitals, you will see this is your 3s2 orbital, this is your 3p orbital, this is your 3p orbital, and this is your 3d orbital. Again, vacant d orbital, right? One, two, three, four, five. Right? So here they are 2 paired electrons in 3s2. Then here you will see that there are 3 orbitals, and in each orbital this is the fashion of arrangement of electrons, right? Like this. And then this is vacant. So this is 3p4 and this is 3d0. So again, this is in ground state. So in ground state, number of unpaired electrons is how many? Can you guess? It is 1. It's 2. Right? Unpaired electrons are 2 in ground state. You can see that these 2 electrons are unpaired electrons, right? In ground state, you will see this. So they can easily gain 2 electrons and make them paired, hence gain an oxidation state of -2, right? But when you excite this state, again, electrons will start shifting to the vacant d orbital. So the 2 pairs will get unpaired, and then after unpairing, you will see that in excited state, you will see that There's one unpaired electron here, one unpaired electron here, unpaired, unpaired. So there'll be two unpaired electrons here as well. So this comes out to number of unpaired electrons as 6, right? So there are 6 unpaired electrons here. Easily they can lose these 6 electrons and form +6 oxidation state also. Clear? So here you can see that after excitation these electrons get unpaired, and maximum number of unpaired electrons you can get is 6. So you can exhibit an oxidation state of +6. Clear? So for sulfur and other group 16 elements, the oxidation number range is from -2 to +6. Are you clear with that? Okay, let's move on. So if you take compounds of sulfur, you will see this. Now in many compounds, you will see that there is an exception, right? For sulfur. Let me take an example. For example, we take the example of H2S2O8. Peroxydisulfuric acid. The name of this compound is peroxydisulfuric acid. Peroxydisulfuric acid. Okay. So if you see here, let's do the normal calculation, right? You know that in a neutral molecule, sum of all oxidation numbers has to be 0, right? Although that's a rule we will discuss later. But you should just know this, that in a neutral molecule, sum of oxidation numbers of all elements is 0 in a neutral molecule. So you know that hydrogen is always +1 per atom. Sulfur we need to calculate, let it be X per atom, and oxygen let me take it as -2. Assume it's all -2, right? So let's do that. So 2 into +1 plus 2 into X plus 8 into -2 should be 0. So you get 2 plus 2x minus 16 is equal to 0. 2x minus 14 is equal to 0. So x will come out to be +7. That's it. We got the sulfuric acid. We got the sulfur oxidation number, right? It's correct. +7? No, it is wrong. Why is it wrong? Think about it. Why is it wrong? Now let's revisit what I just explained to you. The range for sulfur and other group 16 elements is from -2 to +6. -2 to +6. And what are we getting here? We are getting +7, which is not possible for sulfur. The maximum oxidation number of sulfur is +6. How can we get +7? That means we have done some mistake here. What's the mistake then, right? Because oxygen is -2, hydrogen is +1. We've not done any mistake. We have done a mistake. And that is taking oxygen as -2. I told you whenever you're getting oxidation number for the required element out of the range of that element, then that means there is some exception or there is peroxide linkage. Look at the name of this compound. Peroxydisulfuric acid. Peroxy means there is a peroxide linkage, right? And to understand that linkage, let's draw the structure. So this is the wrong method. Let's just mark it. The wrong method. And why have I given you this method? It's because it's a common mistake people will do. So mark that this is wrong, 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 right? So how will we draw the structure now? So structure of peroxydisulfuric acid is this: sulfur with double bond oxygen, double bond oxygen. Then there will be oxygen here. There will be a hydrogen OH basically here. Then there is another oxygen here. This is sulfur. Again, two double bonds with two oxygen atoms and then one OH here. Right? So if you see here, this sulfur has 1, 2, 3, 4, 5, 6 bonds. And here also it has 6 bonds. But see here, look at this. This is your peroxide linkage. Why is it peroxide? Because a single bond between two oxygen atoms, right? That too with -1 oxidation number each. Why? Because sulfur is plus delta and this is minus delta. This is minus delta. This is plus delta. So each of them has one unit of partial negative charge. So it's a peroxide linkage with a single bond between them. Right? That's it. So that means out of the 8 oxygen atoms in this molecule, 2 have -1 oxidation state. Right? Only 6 of them have -2 oxidation state. So let it be X, and let's now solve this again. So if we take all hydrogens to be +1, you know it will be +1. Plus 2 times of X, that's okay. plus 6 times of minus 2, because out of the 8 oxygen atoms, only 1, 2, 3, 4, 5, 6 of them have minus 2 and 2 of them have minus 1. So plus 2 into minus 1 is equal to 0, right? Now solve it. So you get 2 plus 2x minus 12 minus 2 is equal to 0. So this 2 get cancelled. So 2x is equal to 12, which will imply that x is equal to plus 6. And this comes under our range, which is from minus 2 to plus 6. Clear? So it's coming under the range. That means this answer is correct. This method is correct. Clear? So wherever you see that there is the oxidation number of the required element coming out of the range of the oxidation numbers of that element, you should be clear that there is some exception involved. Okay, and if there is an exception involved, it will probably be an oxide linkage, it's a peroxide linkage or some other exception, but in most cases it's a peroxide linkage. In such cases, it's better to draw the structure and check if there is any peroxide linkage. Clear? Are you sure? I hope that's absolutely clear to you, right? So that was an example for sulfur, and was important to tell you because exceptions are always there in chemistry. And then we come to the two last rules of writing oxidation number. The first rule, or the second last rule, is that, which we have discussed many places, we have applied in many places while explaining oxidation number itself, but just for the formality's sake I'm writing it down, that the algebraic sum of oxidation numbers of all atoms in a neutral molecule is equal to, I've just used that, 0. Clear? That's easy. We have used it many places. For example, H2S2O8, here we equated it to 0 because it's a neutral molecule, right? Overall neutral molecule. And the last rule for writing oxidation numbers is in case of ions. So for example, if you have an ion, SO4 minus 2, will still the sum of all oxidation numbers of all atoms be 0? No, in this case it won't be 0. In this case, or in case of any other ion, the sum of oxidation numbers of all atoms is equal to the charge on the ion, not 0, right? So write down algebraic sum of oxidation numbers of all atoms in an ion is equal to charge on the ion. Clear? Let's take an example. For example, sulfate ion, SO4 minus 2. Sulfate ion. So sum of oxidation numbers of all atoms in sulfate ion will be equal to the charge, that's minus 2, so that will be minus 2. Clear? If we take the example of ammonium ion, NH4 plus. In this case also, sum of oxidation numbers of all elements involved or atoms involved will be charge on the ion, which will be plus 1. Right? And using this, if you have an ion, you can find the oxidation number of a particular element in that ion also. Clear? So that's pretty simple. The sum of oxidation numbers of all atoms or elements in an ion is equal to the charge of the ion. And obviously, it can be anything. For example, Fe plus 3, it can be a monoatomic ion also. Here, the oxidation number will be plus 3. If you're taking Zn plus 2, here it will be plus 2 for zinc. If you're taking cuprous ion, it will be plus 1 for copper. If you're taking cupric ion, plus 2, again plus 2 for copper. So basically charge on the ion. That will be the sum of oxidation numbers or oxidation number of that particular element if it's a monoatomic ion. Clear? So with this, we are done with all the rules for oxidation number left after the last video. Thank you very much for joining me. I hope you understood everything in oxidation number. If you have any kinds of doubt, you can post them in the comment section below. Queries, suggestions, everything are most welcome. Thank you very much for joining me. Do like and subscribe, spread the word about the channel, and please follow up the series for the coming videos. In the next video, we will be discussing the concept of oxidation and reduction in terms of oxidation number, right? Once you are done with oxidation number, we have learned all the concept in oxidation number. Now we're going to apply that in redox reactions. How we define reduction and oxidation and other processes in redox reactions or other elements of redox reactions in terms of oxidation number. Thank you very much for joining me. Goodbye. Stay healthy, stay smart, and do keep studying. Bye bye.